Good morning. Good morning, everyone. Today, the previous day, we have actually seen with respect to a model what is bias, what is variance, and we have also seen what is underfitting and overfitting. Both of them are related. So the diagram actually showed one low bias and low variance is actually our target state, and high bias is underfitting, and high variance is overfitting. So we also discussed on how we arrive at these conclusions basing on the given data, and how do we split it into train data and test data, uh, and how do we handle underfitting and overfitting is what we started with. So in continuation to it, one thing we um, discussed with respect to overfitting to avoid overfitting is uh, to avoid overfitting is to do regularization is one thing. We asked also ChatGPT to uh, tell us on what are all the possible ways we can avoid overfitting, and it said regularization, cross validation, early stopping, feature selection, ensemble models, pruning, and data augmentation. I think we have gone through all this, but we definitely have a need to go through it in detail. Mm. So let's start off with the regularization. So that's something that we will cover today, and we'll also try to see the main intent is. So we said, given a data, how to find patterns, how to build machine learning. So how do you build that equation, which actually represents this pattern? And this equation is nothing but your algorithm or model, and then how do you optimize that equation in order to fit in this particular pattern, fit in closer to that pattern so that the loss is minimized. That's what we've looked at it. So now what happened? We are saying the loss is minimized. At the same time, we don't want the loss to be zero, because if the loss is zero, we are going towards overfitting. If it is overfitting, then the performance of the model on the unknown data, which is our actual target. Our target is not the training data, training set or test set. Our target is to predict y with a given unknown values of x. So considering that scenario, we should not be overfitting to the training data set, or else anything that is coming outside the training data set, uh, mm, the model might not perform well. So to consider that scenario, we wanted to have a model which is actually neither overfitting or underfitting, so that it can accommodate the future unknown values and predictive value with minimal loss, right? So to avoid overfitting, what we thought of is um, um, the word overfitting, what we thought of is it has already given us multiple ways. Um, okay, sorry, I'm coming back to this point. So I'm repeating what I'm saying, but what I'm trying to say, the other piece that we are trying to cover today is for a given model, if you build a model, then you evaluate it basing on the test data set. Um, and so we should also communicate to the people, right? So you put a model in place, and then the model should we should be able to communicate it to the people, saying this model I have built, and it comes with this level of accuracy. Somebody is using chat gpt, and even their evaluation will be specific with specific questions or specific pattern. For example, they'll say chat gpt on coding exercise, this is its performance. For chat gpt 3, gpt 4 has this performance levels on coding, or a different scenario of set of questions in, there, and then set of I'll not say questions, but sorry, different different mm, different input criteria will be taken considered for evaluating the particular model on its capabilities. So basing on that, we score it, and then and that's how we compare. So like if you talk of Gen AI, well, there are a lot of large language models that are being published every day. Like Meta has its own model, OpenAI has its own model, um, and then Microsoft has its own model. Um, Everybody, right? There are a lot of people who are fine tuning it, and then everybody comes on the board and says, okay, my model is good, as good as ChatGPT 3. Somebody claims saying my model is outperforming GPT-4. So when this kind of comparison is happening, what they do is they when they to call that their model is performing better than another model, they should have a similar metrics that they need to use. Agree? So these similar metrics are the way they evaluate a model, and all the teams agree saying these are the common metrics using which we evaluate the model, and say that's the right thing to do. But challenge is, um, if you don't get into a common metric, then I'll frame my own set of questions, like my own set of 100 coding questions that are there, and then ask Chat GPT or whatever model that I built, my own model, and then I make sure that it answers all those questions. Like as I said, if it's overfitting the training data set I have, and if my test data set is more aligned to training data set, then actually I'm little biased with what I'm trying to prove, because my model is already overfitting to this particular training data set, and then when I test on this test data set, my evaluations will have give me very good results. But that doesn't mean the objective of AI ML models across the world, or anybody who builds it, um, should be on the prediction capabilities of an unknown data. So on this so um, doing this, if there is no standardization on how we evaluate the models and how we communicate the metrics in a way that people can understand, is not there, then we will not be able to compare it on equal grounds. So people coming back on saying LLMs, my LLM performing better than GPT-4 or GPT-3 or whatever. So we should actually ask them, um, uh, okay, what's the how much data is your model trained on? And that which is something we know already. Second is, you see that um, we know another things about model is number of features and number of parameters as in W1, W2, W3, which gives us weights on each feature and on how to correlate them. So we should say how much amount of data that it is trained on, how many how many parameters are there in your model that actually helps us to understand how much is being considered. Parameters, at times, I need to see, I don't know, but we will also cross check on how the regulation terms also are called parameters or not, but usually they are, because they also vary with respect to model. But they could also be they may not be correlated to features. They may have their own functionalities, or they may have their own behavior, dynamic behavior, based on the incoming data, um, and other detail, right? uh, with that being said, let's ask ChatGPT and move forward on how the remaining techniques which impact regularization, which impact overfitting, are dealt with, and what are the different kinds of techniques. So we'll start off with so our target is, we will not go through this early stopping, feature selection, ensemble methods, pruning, data augmentation, model selection are more approaches, whereas regularization, cross validation are real concepts that we use in um, addressing the model to be generalized. Uh, a model being uh, a model not being either underfitting or overfitting, that middle ground is in a way called generalization, where the model doesn't rely on the training data or the test data so much. It is generalized to an extent, saying it can actually so the model or equation is not really about the data that is there. When we say generalized, it actually is able to answer questions or predict numbers or classify things which are even outside the boundary of this, but is what we were discussing the other day. But I'm just repeating on uh, but I don't want to go deep into it on generalization. But AGI is the next big thing, and in LinkedIn, Andrew has given a post which is very nice. I'll see if I can share it at the end of this video on AGI on generalization concept. So coming to regularization, let's get into regularization and see how the regularization can be defined and what is regularization, and what are different kinds of regularization. So regularization is a technique used in machine learning to prevent overfitting by adding a penalty term to the model's loss function. The penalty term discourages over complex models by penalizing large parameter values. The goal of regularization is to encourage the model to generalize well to unseen by uh, data by balancing the balancing trade-off between model complexity and fit to the training data. There are two main types of regularization commonly used in machine learning. L1 regularization, lasso regularization, or ridge regularization, L2 regularization, ridge regularization. Hmm. Do we have any other regularizations used? It's again going back to this theory, this dropout talk and the L1 to L1, L1, L2, elastic net regularization. Elastic net commands both L1 and L2. Regularization penalties in the last function, it adds again the combination. It's okay. It's again combinations of L1 L2 is what it's saying, but primarily it says L1 regularization and L2 regularization. Okay, so let's look at what is lasso and what is ridge regularization. They're very simple. As I said, what we are driving towards is loss to be zero. Correct. So if loss is zero, that means our equation that is there, which is predicting the patterns, it is exactly predicting the y values uh, as they are given in the training data set. Correct. And that is called overfitting, and we want to avoid overfitting, so we don't want the so one side we train that the y predicted values are as close as possible to y. We try to calculate loss, we try to reduce it and stuff. The other side, what we're saying is we don't want it to be equal to y, because we don't know what's the training data set and what is the unknown data set that is out there, which could be millions or billions of records. Considering that, we don't want it to be equal. Okay, but our overall methodology, our equations, our loss functions, gradient descents, everything is designed in a way, how do we get to that zero value, the loss, how do we approach loss to be zero? um, Either, I mean, technically when you use gradient descent and stuff, you may or may not have losses, you may not reach loss as zero, because the gradient descent approach itself take you to local optimals most of the times, where you go to the least possible scenario and then you take a call whether you want to stay here or you want to still pursue, go beyond that particular local optimal to reach global optimal. So but most of the, we don't know whether there is other global optimal or not. So we might say, as long as the accuracy of this particular local optimal is good enough, we might say that this is good enough for our model requirements that has been given by our customers or somebody, and so we move forward with it. Um, uh, which is okay, because again, as you said, we are not trying to reach zero, um, and zero is definitely a global optimal. Can all models go take you towards zero? May or may not be possible. So consider that scenario. Um, consider that scenario. You usually go for global optimal loss. That will be that will be the best possible scenario for the model kind of stuff. Um, but if your loss could be made zero by y predicted is equal to y values that are there, correct? Because your equation of loss function is more on difference between y and y predicted, correct? So uh, difference between y and y predicted in that loss function, once if I add more uh, value to the loss beyond y predicted and y's difference. So what happens? The loss function will not become zero. So and this additional term that we add is also um, dependent on the model, not y and y predicted, right? So that gives us a leverage on how the model also influences the loss besides the y prediction and y, correct? So that is how they have introduced regularization. So they not only make sure that there is certain loss basing on the y prediction and y, they also make sure the loss is basing on the weights or parameters that we pick up for our equation. So if you see, L1 regularization adds the sum of absolute values of the model's coefficients. Coefficients is nothing but parameters or coefficients are nothing but parameters that we say weights or parameters that we take in the equation uh, to the loss function. It encourages sparsity in the model by driving some coefficients to exactly zero, effectively performing feature selection. The regulation term for L1 regularization is proportional to the sum of absolute values of the model's coefficients. So if it's a lasso regulation, that is L1, famously called L1, everybody and in the data science world, they understand. If you say L1, they'll understand what are you talking about regularization. So here it is nothing but what we do. If you have x1, x2, x3, xn, we will have wi w1, w2, w3, so on wn. So and these weights are used to multiply the x1, x2, x3. So even if you have some feature which is derived from this, we consider them as another feature. For example, x1 square we consider as another feature. X1 into x2 into x3 is another feature. So all them being included, w1, w2 will cover all of them. So uh, w1 to wn are the weights that we use for the model and which will actually help us in um, creating that equation which represents the pattern which is called which we call as a model. So these some of these w1s, if they are taken, those actually represent uh, the overall model's behavior, and those some of the weights can be used as the regularization additional process weight that we want to add to the loss function. So we also actually multiply this with a regularization parameter called lambda there, and this lambda also influences the way the loss function's output is derived, and picking up this lambda value also makes a difference in how much uh, how much what are like you should look at like what percentage of sum of weight should be applied to a model, to the loss function, so that during training, how much it will influence the overall loss. Like let's say you say lambda is 100,000, then what happens is the weights, the sum of the weights influence the overall loss to a major extent. So it will push you from optimizing your model more and more, right? Because this is makes this as a big term, the big value 100,000 into the lambda sum, and basing on that value, the sum of these values, overall loss becomes more. Once the loss is more, you increase your iterations until you reach the optimal value, correct? So basing on the lambda value, we can tweak on how much it will influence uh, to w's and yeah. It's there, it's coming. It's there behind. But what we do? No, no, don't disturb me. Once I'm done, we'll talk about it. Okay, thank you. So that's lambda, and that's sum of W1. So okay, that's lasso regularization. I'll at the end I'll just ask ChatGPT to put it into an equation and then show us. So now come to ridge regularization, L2 regularization. Here I think it's another variant of the regularization. That's all. The um, so the weights um, in lasso are considered as W1, W2, W3, and we do a sum of it. Whereas in ridge regularization, we do a sum of squared values of this model. So that whenever you do square of something, it is more on it is to amplify the magnitude, right? Because if you look at square terms, what will happen as the value grows, it will increase the value higher side, and the value is lower, it will decrease the value. For example, zero point 0.1 square will become 0.01. So that is, the weight is already minimal. The impact of it, the impact or contribution to the loss will become 0.01. 0.04 will become 0.0016, correct? So like that, if the weights are very low, the impact on loss will be very low. Whereas the weights are very high, then for example, if the weights are something like 25, the loss will become 625, whereas the 5 is 25. So the higher the weights, uh, the higher the weights, the higher they contribute towards the output value, because the wi, if it's higher, wi into xi is how it should be, and wi xi will be obviously higher, right? W when it is higher, even though irrespective of x, what is wi? Wi is the weightage of xi, and what it is doing is when wi is higher, that means you are saying the xi feature is so important compared to the remaining features that are there in the data set, that it influences the output so much. So that's the reason wi should be higher. That's what we are trying to say. When there are xis which are influencing your overall output and the remaining features are not being, values are not being considered much, then in the loss function we add either wi or wi square, um, and saying the loss is more. So what happens when you try to derive the next w1, what we do wi new will it be equal to wi old minus, you do derivative of your loss function, right? Cost function. So what happens is you reduce the wi basing on your loss or cost function. So so that's how you see that the wi is reduced basing on your loss, in which loss we are adding wi square. That means if wi is older value of wi is greater than, your loss is higher, and you reduce it further, so that you don't have that kind of a scenario where a specific feature is actually influencing your output so much. It might be good, it might have higher value, but at the same time we want to make sure that your model is not going in a direction saying basing on one feature it's trying to predict everything, right? Because that in the training data set it might have a correlation, strong correlation between a given feature and the output, but in the real world it may or may not have a correlation. And if it is really having that level of a correlation, people would not um, pick up all the features. The domain experts will say, can understand that, okay, this feature actually has stronger correlation. We need not rely on so many features. We'll have this feature plus two or three other features, and then we'll build a model, right? So, um, again, that's the reason or fitting is where w's that we use in the equation to multiply x, w1 x1, w2 x2, w3 x3, so on, wn xn, w's will be reduced in a way that it doesn't go to an extent where it will overfit the particular equation to the required y. That's the that's the circle. So data is given, you build an equation. To build an equation, you assume certain w1, w2, w3. Basing on that equation, you calculate loss and cost. You influence the loss and cost basing on y prediction y and also w's, which are unknowns. Y w is the unknowns, you put them there, and then you use this particular loss cost function's derivation to reduce you to derive your corresponding w new. W new I is equal to w I old minus derivation of this cost function. That's what we have seen in the previous equation. So that in turn reduces w, and you go back to the circle. You again build the equation, you again do y prediction, again do loss cost, again you derive w. So this iteration will keep going until you reach an optimal state. That's how it works. So that's the reason regularization is nothing but including the weights, either wi, sum of wi, or sum of wi squares, as in lasso or regularization, and that would actually influence, that would increase the loss function, and increasing the loss function in turn reduces your w's properly, and also increases the number of iterations. The loss is higher, you increase the iterations that your function goes through, and we should see how it works. So another approach that people have opted for basing on the need is, it's more like it's more experimental, right? Somebody would have used the lasso regularization, that is L1. Somebody would have reached L2 ridge regularization, and it might not have effectively worked on them because of for some reason. So they would have tried a combination of L1 plus L2, that is add both Wi plus W2 square. Like as if we use Wx plus C, and then that has given us a straight line and that is not fitting in. Then we said, oh, okay, why now is W1 x square plus W2 x plus C. So similarly here, what they're doing L1 plus L2, which is nothing but sigma W2 square plus sigma W1 square, and they'll have a lambda multiplying this overall sum. There it has elastic net regularization, which is a combination of controlled by two hyperparameters. So I said we'll multiply one lambda, but it doesn't. It's not one lambda. We use two regularization terms separately for both of them. So it's like alpha and L1 ratio. I don't know what L1 ratio is. Okay, anyways, let's ask ChatGPT to give me equations for L1, L2, and elastic regularizations. Alpha is the overall regularization parameter. P is the mixing parameter that determines the ratio between L1 and L2. So that means maybe the L1 is working good for few and L2 is working good for good for few. So now what they're doing is they're picking up a mixing parameter which says actually how much of W should be considered, how much of WI should be considered. Like 20% of W or sigma W, and 80% of W2 square. So is being considered. So P is a fixing. So alpha and P are picked for elastic net regularization. Okay, I'll show you more. Add these terms to loss or cost forms. I also show how the so as you see to the given loss function there, this is L1 regularization where plus lambda sum of weights is added, and that means this is the equation, right? 1 by 2m into m is number of data set, size of the data set, and we sum of the different squares of it's in summary mean square error is what we do, plus lambda of sum of the w's is what we where we calculate the L1 declaration. And coming to L2, um, it will be the like same equation, but plus lambda into sum of W2 square. That's how the loss is calculated for L2 regularization. Whereas elastic net, if you look at it, it says original loss plus alpha into this equation that is there. That means 1 by 2m sum of plus this equation that is there. And oh, sorry, I missed on the derivation. So what happens? Derivation is what we are using in the W new calculation, right? That the weights are being changed in the grain descent and stuff. So we derive, and then to calculate the new weights, we old weights minus the derivative of the cost function is what we have been using, right? So so in derivation, if you look at it, in the derivation, if you when you um, do derivation of it based on Wi, this loss function now what happens? Previously, it is calculating the derivative of this function, prediction function, loss function. But now with this addition of this derivation will also have lambda into Wi, and this will influence the overall value. And also the lambda Wi square. This should be sum of Wi, like Wi plus the W2, and then this is the square of Wi square derivation is 2Wi, that it makes sense. But whereas for sigma sum of Wi's, it says lambda into sine Wi. I doubt this to some extent. And then here also he says P sine Wi. Derivation of L1 regularization term should be should not be. It's good. Oh, because it has a mod value of x. What it says is if d of x by x is a mod value, it depends on 1 and minus 1. So the values could be minus 1 or 1. Considering that fact, it says either it could be minus lambda plus lambda. So that's what it's trying to say. But it's not trying to say it's uh, in the equation it says um, sine of wi, lambda into sine of wi, not wi. So it says lambda minus lambda plus lambda. It depends on the value of wi. If the wi is negative value, it will be minus lambda. It is positive value, it will become plus lambda. That's okay. Uh, that's fine. Why that is important is, especially if you go with the wi, negative and positive value, few of the parameters influence of the parameter, right, on the actual value. If your wi is positive, that means there is a positive influence on the overall output, whereas if wi is minus, that is there, it's a negative impact on the overall value that is coming in. So we fine tune that particular w's according to the values that are there, and this guy is correct when he says he either uses minus lambda plus lambda, whereas um, in lasso, it's only plus or minus lambda is the output of the derivation that influences the new w. Whereas the regularization, it is 2 multiplied by um, yeah, well, this one. So it is 2 multiplied by lambda and wi. So wi term is also part of the derivation, and it reduces the thing. Whereas in elastic net regularization, as it has a combination of both of them, it will become alpha into minus r plus p, regularization of the L1, plus 2 into 1 minus p of into w. So like this, alpha pw sine of w plus 2 into alpha 1 minus p into w. This sum of these two terms will become your derivation chemistry. So, oh, we targeted of covering regularization, cross validation, and also we thought of looking at accuracy and stuff, but only regularization itself has taken this long time because we were actually explaining more on the background. Tomorrow we'll try to avoid expanding the background terms so much, and we will try to jump in and move forward, so that because in case if you want to look at back things which are already explained, we'll just refer to the previous video. So we'll start with that. Stop sharing. Go to this. Okay, bye guys. I think we have seen regularization to the detail, which is good, which is useful, and we'll cover the remaining topics tomorrow. We'll study the remaining topics tomorrow.